The Sun has been sending its powerful rays to planet Earth for billions of years. Humankind has always relied on the light and the warmth of the Sun. It alone makes life and growth possible. That is why we revere the Sun and worship it. The Sun also emits enormous plasma storms. These eruptions are energy-charged winds which threaten to cripple our electricity supply and cause a worldwide blackout.
The infrastructures and technologies we use are at risk because of space weather.
We are grateful to have the Sun, but it is also a major threat to us, especially through solar storms.
These storms occur repeatedly at irregular intervals of up to several years. The last time was in 2017, but the Earth was lucky. The plasma cloud missed our planet. To solve the mystery of solar storms, scientists at NASA are developing a probe that will fly closer to the Sun than anything before it. So will scientists be able to study the dangers posed by solar storms, or are we entirely at their mercy? Volker Bothmer is an astrophysicist. He studies the Sun. He is heading Germany's contribution to the new type of probe. Sensitive instruments that can withstand extreme forces and temperature will have to be mounted on all sides. Above all, a camera will be essential for observing the solar storms. And that is Volker Bothmer's responsibility.
We can warn of solar storms if we have the appropriate space observation tools. Some forms of observation can only be carried out from space. They call for satellite technologies, onboard cameras, which can provide lead times, because it's on these lead times that mitigating possibilities depend.
The mission is designed to help create early warning times, which will enable us to be better prepared for solar storms. This, however, calls for research into the origins of solar storms and answers to the questions of why they accelerate at such staggering speed. Because solar storms are so fast that they only need 1 or 2 days to reach the Earth. So they travel at 7 million kilometers an hour. By comparison, a full-blown tornado rages at a speed of 500 kilometers an hour. Never before has a mission been mounted to fly so close to the Sun. It's a bold undertaking, so the probe will have to set totally new standards. Scientists at NASA have called the project the Parker Solar Probe.
Parker Solar Probe will be flying about 6 million kilometers from the solar surface. If this is the Sun-Earth distance, Parker Solar Probe will be flying this close to the Sun.
The Parker Solar Probe will approach the Sun to within 4% of its distance from the Earth, an ambitious goal with an uncertain outcome. But it is the only way to explore how and when solar storms form.
There's no doubt that a powerful solar storm will occur soon. It's merely a question of when, and we want to be as well protected as possible.
Because when a solar storm hits us unawares, power grids experience uncontrollably high temperatures, which can even melt the biggest transformers in substations. This happened in South Africa, for example, in October 2003. A sudden and extensive power failure disables waterworks and their pumps. Pipelines can no longer transport oil because they too need electricity. Ultimately, prolonged outages resulting from transformer damage bring virtually everything to a standstill, because even emergency generators have only a limited running time. The result, total breakdown, including bottlenecks in the food supply. It's a scenario scientists warn of. Normally, the Earth's magnetic field protects us from solar particles, but when the solar wind turns into a storm, this protection is no longer sufficient. Then the plasma mass pushes against the magnetic field and compresses it. Geomagnetic measurements enable the solar winds to be detected. Roman Leonhardt from the Konrad Observatory in Austria has been recording the changes in the Earth's magnetic field for many years. Protected from external influences, here at a geophysical research facility 50 kilometers southwest of Vienna, Leonhardt has created ideal conditions for his measuring instruments.
The Earth's magnetic field is normally rather calm, there's hardly any movement. But when a solar storm hits, we clearly register it.
These measurements of the Earth's magnetic field are important for assessing the data on solar storms recorded by satellites.
Satellites also measure solar storms, not as accurately as the equipment here, but much earlier, of course. And a comparison of the two measurements gives us an idea of whether one day we will be able to predict solar storms.
The more data that is available on a solar storm, the higher the chances of forecasting where and with what power it will hit the Earth, and how much dangerous energy it will generate. The big question is, at what point will a solar storm overload the power grid?
These currents can seriously threaten the power grid and ultimately result in a breakdown or a blackout. If we know the distribution of these currents in advance, we can work out appropriate countermeasures and then react accordingly in an emergency.
Professor Renner has developed a system for determining what impact the extraordinary currents will have on the power grid. It is based on the geomagnetic measurements made here at the observatory.
We calculate an electrical field and subsequently the currents in the transformers. When this curve here rises, it means that the transformer is threatened and ultimately the power grid as well.
Solar winds impacting on the Earth also become evident in another way. Magnetic field lines on the side of the Earth facing away from the Sun combine and enable electrically charged particles to flow into the Earth's atmosphere. There they excite atoms to glow. So it is actually the effect of solar storms that produces the polar lights. Sometimes they are red, and sometimes green. With powerful solar storms, these lights are not only visible near the poles, they migrate further and further towards the equator.
In 1989, for instance, I could have seen the northern lights, but I missed them because I was looking in the wrong direction. Then in 2003, we had another solar storm. Through satellite data, I saw in my study that the solar wind was becoming stormy. I worked out that at home in an hour's time, I might be able to see the northern lights. I went out onto my patio and even checked my compass because I'd expected a major interference. Around midnight, I actually felt like going to bed, but then I remembered what had happened in 1989 when I looked in the wrong direction. Not again, I thought, and had a walk around the house. And I was lucky. For half an hour, I really did see the northern lights.
It is just as rare for us to have the chance to see an eclipse of the sun. When the moon moves in front of the sun, we see a bright halo around it, known as the corona. And this is where the Parker solar probe will be flying to, because it's where the solar winds are generated. And it is precisely here, too, that something unusual happens.
If you have a campfire, the further away you move from it, the cooler it gets. That does not work for the solar corona. When you look at the surface of the sun, the temperature is about 6,000 degrees. Move up about 2,000–3,000 kilometers, and the temperature of the plasma will jump to more than 1,000,000 degrees. That is completely counterintuitive. It should not be that way. But the sun magically does things that are out of the ordinary. And one of them is what we call the coronal heating. The corona is more than 300 times hotter than the solar surface.
It is vital for scientists to understand why the corona heats up. For that reason alone, Volker Bortmer has to equip the probe with a special camera to take pictures of the corona. That is why he is off to see his colleague, Russell Howard, who works for NASA in Washington.
Washington, D.C., please.
That would be nice. Is it a business trip?
Yes, I've got a meeting about flying as close as possible to the sun with a camera.
That will be far too hot for my liking.
Yes, 1,700 degrees is a bit much. But we need the camera on our solar mission in order to explain some of the measurements.
So the measuring equipment on the probe itself will be backed up by the camera, so to speak.
Exactly, there are some things I need to discuss with Russell Howard. He's still not convinced we'll achieve what we've planned.
So he needs persuading, eh?
He does.
Afterwards, then, the pictures will tell you exactly where the probe has been?
Of course.
At this point in time, at NASA in Washington, they still haven't decided whether, because of its limited load-bearing capacity, the probe will have a camera on board. However, Volker Bortmer has sound arguments to put forward. He hopes for support from his American colleague Russell Howard. United by their love of the sun, the two have been good friends for many years.
Hi, Volker.
Hi,
Good to
Russ.
see you. Good to see you.
Same for me.
How have you been?
Oh, it was a good trip coming.
Good. Before we talk about the camera, I wanted to show you something that I found a little while ago. It was in a book, and let's try to find the book. It's about so big. It's blue. It may be here. No. Yes. I put it down here. Here it is. So it's in theoretical astrophysics.
Oh, that's a German book.
Yes. It's a quotation. It's in German, so excuse my poor German. Fragt man mich, ob es in meiner Natur sei, die Sonne zu verehren. So sag ich abermals durchaus.
Oh, that's Goethe.
It's Goethe, yes. And he's talking about his feeling toward the sun. I feel the same way about the sun.
Sun worship, devoting mind and body to the sun. What better way to start than with a salute to the sun? The sun salutation is one of the most popular exercises in modern yoga. It is said that whoever performs the sun salutation first thing in the morning will stay healthy and lead a happy life. And anyone who starts the day with the sun has a good chance of spending the rest of the day in a harmonious rhythm. Here, the dangers of solar storms seem millions of miles away.
Let me give you a call back in a little bit. Thanks very much. Bye.
In the end, Russell Howard is also in favour of a camera on board the Parker solar probe. His initial design for the space camera, an instrument for taking special images.
I actually love photography. I've always loved photography. So this is amazing. My personal goal was to have an instrument that could see the sun, see the corona, not the sun, but the solar corona.
Howard wants the camera to have a viewing angle that will capture the corona around the sun, so it will need a specific position on the probe.
Very important that we be above. Here we have a model of the Whisper instrument, and we'd like it to be in this position on the spacecraft, and just about so.
The camera will be extremely light sensitive, So Boortma and Howard must make sure that no sunlight can shine on the camera while it is photographing the corona.
Now we can put the spacecraft in the beam of the sunlight.
I think we're set. Could you switch off the light, Volker?
Yes.
And we'll do a little test.
The camera must be shielded from sunlight because it has to observe structures in the solar wind and the corona that have only a millionth of the sun's luminosity.
The sun's heat is also so dangerous that the camera must always be protected by being in the shade. After a lengthy discussion, a concept is finally agreed on. The camera can now be built. Because of the two wide-angle lenses, it has an unusual shape. The camera's cover opens to the side. It protects the lenses installed under it, but when the camera is taking photographs, the exposed lenses will face in the direction of flight, and dust particles in space will strike them at high speed, so damage will be inevitable. It's hard to predict how high the impact will be. After all, this will be a flight into new territory. But Boortma and Howard can't risk the camera being blinded. They need glass with a particularly resistant surface. So various types are tested.
In terms of the depth of the impact and the size of the impact. So can you see any with the naked eye?
Yeah, I can see some spots, the larger ones.
Uh-huh. Oh, that's interesting.
And I can compare it with
Let me take a look.
the other two types. So multiple small clouds, it looks like.
So what'll happen is when an event is coming out, we're going to see it, and then the spacecraft will run into the event. We're going to be flying through that sort of harsh particle environment. I mean, that's a risk. It's sort of like dust on your car window that you get these impacts, and if you have a very old car, you have a lot of dust impacts, and when you're driving into the bright sun, it's really difficult to see. So it's the same problem that we have.
Boortma and Howard have already had plenty of experience of building space cameras together.
Very good stereo.
Back then, it involved photographing the solar wind in 3D.
Yeah, that would be. What kind of cameras do you suggest to have on board?
That's never been done before, so that would
we don't
really
have
be nice.
such a camera yet.
We don't have such cameras, that's correct.
The mission in 2006 sent up two satellites at once, Stereo A and Stereo B. This enabled the solar wind to be photographed simultaneously from two sides, however, only from a great distance. Tenerife, situated 2,400 meters up at the foot of the Pico del Teide, is the solar telescope Gregor. Conditions here are ideal for observing the heavens. As the biggest telescope in Europe, Gregor will be able to supplement observations by the Parker Solar Probe from the Earth. Air turbulence in the atmosphere is actually a hindrance to observing the Sun from the Earth, but Lucia Kleint has a special reflector in her telescope that can counterbalance this distortion. What's more, from here the Swiss scientists can observe the Sun around the clock.
There are only certain times when the Parker Solar Probe is close to the Sun that will be good for taking measurements. We can measure the Sun every day.
But the telescope's big advantage is its particularly high resolution. It enables the astrophysicist to make a detailed study of the sunspots.
The Sun has an 11-year cycle. In other words, every 11 years it has a particularly large number of both coronal eruptions and sunspots. Scientists have known about this cycle for centuries. In the past, it was thought that there was something evil about sunspots, because they were always accompanied by disturbances and solar storms. But today we know that sunspots are simply cooler areas on the Sun's surface.
The sun's surface around the spots resembles a pot of boiling water. Hot plasma rises up from the depths, cools and sinks again. This produces a lively pattern of light-coloured bubbles with dark edges, findings made possible by fine adjustment and cooperation.
In solar physics, we always try to combine all telescopes and space probes, because only by collating all the data from them can we really learn about the sun.
If such comprehensive observation had been possible in 1989, Canada might not have experienced the catastrophic power cut which affected 6 million people. In Quebec, at a winter temperature of -7 degrees, not only did the district heating fail, suddenly the children's hospital also had no electricity, with several operations in progress. Transformers could not cope with the massive power surges. As a result, Austrian power company APG now operates special transformers designed to counterbalance the dangerous direct current of the solar wind. But it will still be many years before such transformers are widespread. For cost reasons, power companies can only install this type of transformer here and there, hardly a satisfactory situation.
A solar wind striking the Earth is not a spatially confined phenomenon, but an extensive one. So we must assume that several transformers will be affected. However, when numerous elements fail simultaneously, naturally there are outages. In the worst case, there's even a blackout.
APG is developing an emergency plan for such a scenario.
Our research is geared to finding measures we can apply in the event of a solar wind. Our operational personnel are being trained to know how to act in the event of such a scenario and not be surprised by it.
Volker Bothmer also wants to make sure that solar storms don't become nasty surprises. Solar measurement data, he felt, shouldn't only be accessible to scientists. There had, he reckoned, to be an uncomplicated way of enabling anyone to gain a quick idea of conditions on the sun, so he developed an app which portrays NASA's solar observations directly.
I wanted to develop an app for space weather because it's a topic which is becoming increasingly important for our society. Now anyone can have access at any time to information on what the sun is doing and what consequences that could have for the next few days.
Reading coffee grounds to obtain information on solar storms is not an alternative. The scientists base their forecasts on validatable data, even though they reach their limits in doing so.
The sun is so complex there is no way it can be simulated in its entirety. You have to imagine the sun's magnetic field as a rubber band running from the north to the south pole. However, because the sun rotates faster at its equator than at its poles, this rubber band gets tangled, and that's precisely when solar storms occur.
The magnetic field lines bind tons of plasma, but if they get so tangled that they burst, this plasma is hurled out into space.
We don't really know whether it will ever be possible to predict solar storms. If solar storms are totally chaotic, we'll never be able to forecast them several days in advance.
Solar storms affect not only the Earth, but also the spherical zones around us. That, for instance, is where GPS satellites orbit, and they form the basis of our navigation systems.
If the GPS system is disturbed by solar storms, the position being read changes. So although you will know that you are now in Europe or in America, you will not know if you are in front of the runway or next to it.
Inaccurate navigation data, a nightmare for pilots and safety air traffic where everyone is dependent on precise signals. It's a problem with life-threatening risks. In 2003, for example, Japan briefly lost control of 2 GPS satellites. GPS signals move through the ionosphere, which surrounds the Earth like a shell. If it is deformed by a solar storm, the GPS signal is also adulterated.
When the last powerful solar storm occurred several years ago, around 60 aircraft were not allowed to take off. An aviation radar in Scandinavia broke down.
Several American airlines already take space weather into account, and ICAO, the International Civil Aviation Organization, recently set up a work group to specify when aircraft must be grounded.
We need concrete space data for forecasting, and then corresponding standards for worldwide transmission of what space weather conditions can be expected, what their specific effect will be, and what steps should be taken. This will all have to be developed in the years ahead.
Nature has its own battle with space weather. Some birds and some insects, like the monarch butterfly, have their own navigation system which functions on the basis of the Earth's magnetic field and enables them to fly unerringly to their winter quarters. However, if the Earth's magnetic field is disturbed by a solar storm, the sensitive butterflies are totally disoriented and flutter around in utter confusion. In autumn, when it climbs no higher than 52 degrees, the sun gives the signal to migrate. Then millions of monarch butterflies in North America embark on a flight of more than 3,000 kilometers to Mexico. Every year they land precisely in the same place, on an area of just 20 hectares. Settling on the pine trees, they enjoy the sun's warmth for the next 5 months. Then, just as purposefully, they set off on their journey back. But they lack the strength for the long flight. The monarch butterflies will never reach their distant home in North America. The Parker Solar Probe will also need a vast amount of energy for its long flight. First of all, it will fly to far-off Jupiter to benefit from its gravitational forces, which will give the probe an injection of momentum. It will then head for the Sun. But this has long been a controversial concept because the Jupiter leg of its journey will require the probe to have its own nuclear power plant as a source of electricity, an enormous investment, even for NASA.
You ready for the meeting?
Yeah.
Yeah, let's go, guys.
All right.
I think we have to discuss this.
I think we could. Come up with some new ideas.
Bortmer is discussing the flight route once again with the NASA team. Too costly, they say.
At the time, we had a meeting with the director of NASA. He said we ought to think about a different technology, a different mission concept. Firstly, to reduce the cost. Secondly, to guarantee more measurements. And thirdly, to make a radioactive battery unnecessary. And we didn't want the solar mission as a whole to be at risk of being scrapped.
So a new flight path had to be found. Howard and Bortmer had to consider which plan could function as an alternative to the Jupiter route.
We're going to change the trajectory of our satellite by hitting Venus and then go directly to the Sun.
I like to see this.
Okay, so here I am sitting on my rocket. I have to get the speed right too.
Now we have to think whether we're getting close enough to get the right measurements.
This way, we'll be able to make several passes around the Sun. Sometimes we go right into the
I
cup.
think that's the way that we should go for this scenario rather than go to Jupiter. That's really convincing.
thing in space is that things don't slow down because of friction. They just keep on going.
It looks as if you're convincing me to drop the Jupiter gravity. So I should go there to make the flyby happen. Indeed, it works.
Yes, that was very good. Very good. Excellent.
That scenario will work.
But let's not go there on the first try.
Scientists at NASA finally agree that the probe should fly to Venus, be slowed down in passing the planet, and head on to the Sun. First and foremost, this will increase the available measuring times because the Parker Solar Probe will orbit the Sun not twice, but 24 times. ESA, the European Space Agency, is also working on solving the mysteries of solar storms. Its scientists have spent 12 years developing the agency's own probe, the Solar Orbiter.
The special feature of the Solar Orbiter is its trajectory, which will take us out of the solar system's plane. All our observations so far have been from a terrestrial perspective, partly because all the planets in our solar system orbit the Sun, as if they were all on a disk, and it takes a lot of effort to fly out of this ellipsis. What we are lacking, we think, is data from the Sun's poles. And the only way of seeing the poles is to fly out of the ellipsis and observe the poles from above.
Daniel Muller is coordinating the various teams working on the Solar Orbiter. Here too, one of the biggest challenges is to ensure that the €300 million probe will be able to withstand the heat. In France, for example, various materials have been undergoing tests for years.
We've managed to develop special materials and methods for these instruments which will prevent them melting. This will enable the instruments to function and produce the expected results.
10 different measuring instruments have been developed for the Solar Orbiter. One of them enables the X-rays emitted by the Sun to be seen. For this instrument, astrophysicist Lucia Kleint uses an optical lattice the X-rays can pass through. It's an important building block for studying solar storms.
In visible light, you only see the effects of solar eruptions, but with the X-rays, you can search for the causes. Our instrument has 2 metal lattices, and on this metal lattice, you can see a pattern resulting from the X-rays. This pattern is unique depending on where the eruption occurred on the Sun's surface, so we can say exactly where the particles came from.
Localizing the eruptions is a special technological feature of the ESA's Solar Orbiter. Since this is something NASA's Parker Solar Probe can't do, the two probes will complement each other. Assembly has to take place quickly. A good year before the launch date, the probe assumes its final form, complete with all details. Finally, it is encapsulated. At the same time, all phases of the launch have been tested over several months at the control center. Finally, in February 2020, the Solar Orbiter is launched from the NASA Space Center in Florida.
Chamber pressure on the SRB looks good. Engine operating parameters on the RD-180 also look good.
The Solar Orbiter will be in flight and transmitting data from the Sun for 7 years. It has 10 different measuring instruments on board, all from various European countries.
Personally, the Solar Orbiter means a lot to me, because it's shown that highly complex things can be built by many people from different fields, all working together. Over the last 12 years, I have seen so many people invest so much of their lives and so much blood, sweat and tears to achieve the greatest possible success.
For NASA scientists too, being able to study solar storms is a long-held dream. Even in 1958, The year NASA was founded, many were already thinking of a mission to the Sun. Back then, Assistant Professor Eugene Parker first postulated the bold theory of a solar wind. Putting it to the test would have required a solar mission.
We knew that the space age was coming and that we would soon test directly whether there was a solar wind. It was just a matter of a few years of time.
The fact that it wasn't so easy to prove the existence of solar wind lay not only on the impossibility of such a mission, but also on the fact that established scientists disputed such an existence. Eugene Parker had postulated something totally new and had to hear a great many negative comments.
The referee suggested I go to the library and read a book about this, and I wouldn't make such stupid statements. C log R.
Eugene Parker's calculations are still correct today. Back then, though, it was all new. He maintained that the solar wind was a complex system involving magnetic fields, plasma, and energy-rich particles.
I don't know why it's so difficult for some people who just don't see things in a new way when the time changes and the concepts change. They don't change with it. They resist the change and they dislike it intensely. And I always thought that a good rational change is fun.
Now, over 90 years old, astrophysicist Eugene Parker can at last harvest the fruits of his work. 60 years after Parker discovered solar wind, for the first time measurements and photographs in the middle of the corona have been made possible. The space probe was named the Parker Solar Probe in his honor. Flying too close to the sun has always been dangerous, even in Greek mythology. This painting by Martin Reichardt, which dates around 1620, shows Icarus together with his father, Daedalus. To escape from prison on Crete, they made themselves wings from feathers stuck together with wax. But when Icarus flew too close to the sun, the wax melted and he plunged into the sea.
Daedalus had warned his son not to fly too high.
But he did, and you can see the wax dripping down.
But Daedalus is doing fine.
Icarus didn't know that the sun can also be dangerous.
The heat environment close to the sun is so huge. I mean, it's so overwhelming that you put something there, it will melt in seconds.
The sun is unimaginably hot. The temperature at its core is 15 million degrees. This energy is carried outwards by particles in a process that can last for hundreds of thousands of years. On their long journey outwards, the particles lose their energy and become visible light. Scientists have found that this visible surface still has a temperature of 6,000 degrees.
Plus, after all these tests, I think we will get in a much better shape than Icarus when he started to fly towards the sun in Greece on the Crete island.
He never did a thermal test.
Great, so let's go to Crete or Greece and enjoy some wine, sun.
Sounds good.
And
Some
not get
little
burned.
ouzo, maybe a little ouzo?
Yeah, Fuso too.
The fact that the space probe will not melt is due mainly to its heat shield. Made of carbon compounds, it is a mere 11 centimeters thick, but that is sufficient to protect the measuring instruments behind it. The temperature on the sun-facing side of the heat shield will be up to 1400 degrees, whereas the shaded side will be roughly at room temperature. In addition, a water circuit will cool the solar cells to prevent them from overheating. Temperature, by the way, is not the same as heat. Temperature is merely a form of measurement, whereas heat is the transfer of energy. In gaseous heat, the energy particles are distributed so thinly that there is hardly any contact with them. So although the temperature in the corona is between 2 and 3 million degrees, this heat will not pose a threat to the probe. At NASA, the Parker Solar Probe is almost ready. Just a few last tests are needed. The success of the solar mission will depend to a large extent on whether the camera developed by Howard and Bortmer really does prove stable enough for a space flight. Weighing 10 kilograms, it has an extremely robust design, but a rocket launch is so violent that a special vibration test is necessary. This is a critical point for all space missions. That is why there is an extra laboratory here where vibrations can be simulated.
Part of constructing a space experiment is proving that it's going to work in space, that it's going to survive this very violent launch. I mean, I can't imagine being an astronaut sitting on top of a rocket during the launch. It's just, that just boggles my mind that somebody would do that, honestly. It's a very tough ride, so that the vibration is part of the launch sequence.
The cover on the camera could also become a problem. If it fails to open, the lenses wouldn't be able to see anything. So the Parker Solar Probe is tested time and again.
Three months before the launch, we discovered that we have a problem with a set of heat sensors on the spacecraft. We had 87 of them on the spacecraft, and just a few of them, and when I say few, I think it's 3 or 4 failed. I remember that day vividly. It was absolutely electrical. And the team was so nervous. I mean, we are seeing the finish line, but we may not cross it. And that was not a good feeling to have. But the team is so great. It's so, in a month and a half, they came up with a solution. We installed a new system of heat sensors in the spacecraft. But on top of that, we figured out what was the root cause of the failures of the old system. And now in the spacecraft, we have 2 systems of heat sensors. And they are working both together beautifully without problems.
The Cape Canaveral Launch Complex in the United States. The biggest available rocket, the Delta IV Heavy, is being put in position for the launch. Only the Delta IV will be able to give the probe sufficient momentum.
Six, 5, 4, 3, 2, 1, 0. Liftoff of the mighty Delta IV Heavy rocket with NASA's Parker Solar Probe.
For Eugene Parker, on this day in 2018, a lifetime's dream has become reality. The further the probe moves away from the Earth, the more difficult communication with it will become. Close to the Sun, communication will cease completely.
Operating Parker Solar Probe is one of the most challenging aspects of the mission. When we get into the encounter mode, when the spacecraft is very close to the sun, it has to be 100% autonomous. And by that I mean, if there is something that happens with the spacecraft, it has to solve it by itself. We cannot intervene, we cannot do anything for it.
A worldwide network of antennae will make data exchange possible. Despite this, contact will only be possible if the Earth and the probe are in a certain constellation with each other.
So basically, when we get in the encounter mode, the only way to communicate with the spacecraft is what we call beacon tones. And beacon tones are very limited bits of telemetry that tells us the overall state of the operation level of the spacecraft. And they are emitted by what we call the fan beams. And these fan beams, they emit basically 180 degrees wide beam of radio, and the Earth has to be within
Earth is in this plane.
that plane, yes, in order to detect it.
That's very good.
And hopefully today we'll get to beacon tones.
So the antenna is tucked behind the heat shield.
Yes, it should not see the direct sunlight
at all.
It has to operate in room temperature.
Okay. So let's look again.
Yeah. So whenever beacon tone.
So there it's displayed up there.
Yes.
For the scientists, it is now a case of waiting, having a cup of tea until the Parker Solar Probe can send back the first data. The journey will take 88 days. 88 days and nights, which will pass in the rhythm of the sun, just like the last few million years have done. In this solar rhythm, nothing has ever changed for life on Earth. Solar time is the time shown by a solar wristwatch. Engineer Carlo Heller develops such watches. He and his daughter know the rhythm which the sun dictates, how it divides the day into hours and minutes. The watches, clocks and sundials manufactured here show that our official summer and winter times rarely correspond to real solar time. Yet solar time is decisive for our bodies.
The sun rises in the morning and reaches its zenith at noon. This is defined as 12 o'clock solar time, real solar time. Noon also divides the day into two equally long halves. And it's with solar time, with 12 o'clock noon, that our inner clock is centered again and again.
Our bodily functions are geared to this solar time. Accordingly, solar timepieces show which phase of the day we are in.
The sun gets up. Our blood pressure and body temperature rise. We wake up. And in the evening, when the blue light portion diminishes, melatonin is released. We go to bed, and the next morning everything starts anew, thanks to the sun.
Just how deeply rooted this eternally uniform rhythm is anchored in nature is also shown by plants.
Like all living creatures, flowers also have an inner clock. They open and close their petals according to the time of day. And to ensure that this always takes place in step with the solar time, here too, sunlight determines the rhythm.
The power and radiance of the sun are immeasurable. There is no doubt that we live in its atmosphere, as scientists put it, which makes studying its mysteries with all possible means even more urgent.
We will observe the sun with telescopes, but we will also measure the sun's breath, the solar wind as it passes the satellite. And if we really manage to achieve this combination, and also have data from the Parker Solar Probe at our disposal, we really will be able to establish a causal chain of cause and effect, and thus come to a better understanding of our place in the solar system.
So far, the NASA mission has also gone according to plan. The Parker Solar Probe always transmits its signals to Earth on time. There is always a lot of tense excitement in the control center when new data are expected, because the special camera designed by Howard and Bodmer is already transmitting sensational pictures. Even after the first phase of the mission, scientists realize that the image of the Sun we have had up until now is far too simple.
Before the launch, we had a workshop to basically to make predictions of what Parker Solar Probe is going to see in space. All the predictions are completely wrong. What we are seeing in the data is new phenomena that we never seen in the solar wind before.
It is now clear that the Sun's magnetic field lines do not spread out evenly, but spontaneously change their direction within seconds in zigzag fashion, possibly an important building block for understanding solar storms. The two probes will transmit data to Earth for several years. Each orbit of the Sun will produce new findings. When the Sun sneezes, the Earth catches a cold, even if we might forget that in our everyday lives.
When the weather is nice and warm, which of course is triggered by sunlight, I go swimming and don't think about solar storms.
We'll now do a dynamic Surya Namaskara B sun salutation from Ashtanga Yoga, with 2 warrior variations.
For all of us who orbit the Sun, it is most definitely the source of light and life, a power center full of mystery and fascination. Science will try to give us answers to pressing questions, to protect us from the dangers which emanate from the Sun.